Hello friends, in our last discussion we talked about the memory organization of SRAM and DRAM. In today's discussion we shall be talking about the read-only memory. A ROM contains permanently or semi-permanently stored data which can be read from the memory, but either cannot be changed at all or cannot be changed without specialized equipment. A ROM stores data that are used repeatedly in system applications such as tables, conversions or programmed instructions for system initialization and operation. ROMs retain stored data when the power is off and are therefore non-volatile memories. The ROM family. Figure shows how semiconductor ROMs are categorized. The mask ROM is the type in which the data are permanently stored in the memory during the manufacturing process. The PROM or programmable ROM is the type in which the data are electrically stored by the user with the aid of specialized equipment. Both the mask ROM and the PROM can be of either MOS or bipolar technology. The EPROM or erasable PROM is strictly a MOS device. The UV EPROM is electrically programmable by the user, but the stored data must be erased by exposure to ultraviolet light over a period of several minutes. The electrically erasable PROM can be erased in a few milliseconds. The mask ROM. The mask ROM is usually referred to simply as ROM. It is permanently programmed during the manufacturing process to provide widely used standard functions such as popular conversions or to provide user specified functions. Once the memory is programmed, it cannot be changed. Most IC ROMs utilize the presence or absence of a transistor connection at a row oblique column junction to represent a 1 or a 0. Figure shows MOS ROM cells. The presence of a connection from a row line to the gate of a transistor represents a 1 at that location, because when the row line is taken high, all transistors with the gate connection to the row line turn on and connect the high to the associated column lines. At row oblique column junctions where there are no gate connections, the column lines remain low when the row is addressed. A simple ROM. To illustrate the ROM concept, figure shows a small simplified ROM array. The blue squares represent stored ones and the gray squares represent stored zeros. To understand the basic read operation, let us assume that when a binary address code is applied to the address input lines, the corresponding row line goes high. This high is connected to the column lines through the transistor at each junction or cell where a 1 is stored. At each cell where a 0 is stored, the column line stays low because of the terminating resistor. The 8 data bits stored in the selected row appear on the output lines. For example, ROM in figure is organized into 16 addresses, each of which stores 8 data bits. Thus, it is a 16 into 8 ROM and its total capacity is 128 bits or 16 bytes. ROMs can be used as lookup tables for code conversions and logic function generation. Internal ROM organization. Most IC ROMs have a more complex internal organization than that in the basic simplified example just presented. To illustrate how an IC-ROM is structured, let us use a 1024 bit device with a 256 into 4 organization. The logic symbol is shown in figure. When any one of the 256 binary codes is applied to the address lines, 4 data bits appear on the output if the chip enabled inputs are low. Although the 256 into 4 organization of this device implies that there are 256 rows and 4 columns in the memory array, this is not actually the case. The memory cell array is actually a 32 into 32 matrix as shown in the block diagram. 5 of the 8 address lines A0 through A4 are decoded by the row decoder, often called the Y decoder, to select one of the 32 rows. 3 of the 8 address lines A5 through A7 are decoded by the column decoder, often called the X decoder, to select 4 of the 32 columns. Actually, the column decoder consists of one of 8 decoders. The result of this structure is that when an 8-bit address code A0 through A7 is applied, a 4-bit data word appears on the data output when the chip enable lines are low to enable the output buffers. This type of internal organization or architecture is typical of IC-ROMs of various capacities. ROM access time. A typical timing diagram that illustrates ROM access time is shown in figure. The access time TA of a ROM is the time from the application of a valid address code on the input lines until the appearance of a valid output data. Access time can also be measured from the activation of the chip enable input to the occurrence of valid output data when a valid address is already on the input lines. Programmable ROMs. PROMs are basically the same as mask ROMs once they have been programmed. As you have learned, ROMs are a type of programmable logic device. The difference is that PROMs come from the manufacturer unprogrammed and are custom programmed in the field to meet the user's needs. A PROM uses some type of fusing process to store bits, in which a memory link is burned open or left intact to represent a 0 or a 1. The fusing process is irreversible. Once a PROM is programmed, it cannot be changed. Figure here illustrates a MOS PROM array with fusible links. The fusible links are manufactured into the PROM between the source of each cell's transistor and its column line. In the programming process, a sufficient current is injected through the fusible link to burn it open to create a stored 0. The link is left intact for a stored 1. 3 basic fuse technologies used in PROMs are metal links, silicon links and p-n junctions. Metal links. Metal links are made up of a material such as nichrome. Each bit in the memory array is represented by a separate link. During programming, the link is either blown open or left intact. This is done basically by first addressing a given cell and then forcing a sufficient amount of current through the link to cause it to open. Silicon links. Silicon links are formed by narrow notched strips of polycrystalline silicon. Programming of these fuses requires melting of the links by passing a sufficient amount of current through them. This amount of current causes a high temperature at the fuse location that oxidizes the silicon and forms insulation around the now open link. Shorted junction. Shorted junctions or avalanche induced migration technology consists basically of two p-n junctions arranged back to back. During programming, one of the diode junctions is avalanched and the resulting voltage and heat causes aluminum ions to migrate and short the junction. The remaining junction is then used as a forward biased diode to represent a data bit. EPROMs. An EPROM is an erasable PROM. Unlike an ordinary PROM, an EPROM can be reprogrammed if an existing program in the memory array is erased first. An EPROM uses an N MOSFET array with an isolated gate structure. The isolated transistor gate has no electrical connections and can store an electrical charge for indefinite periods of time. Two basic types of erasable PROMs are the ultraviolent erasable PROM and the electrically erasable PROM. UV EPROMs. You can recognize the UV EPROM device by the transparent quartz lid on the package as shown in figure. The isolated gate in the FET of an ultraviolet EPROM is floating within an oxide insulating material. The programming process causes electrons to be moved from the floating gate. Erasure is done by exposure of the memory array chip to high intensity ultraviolet radiation through the quartz window on top of the package. The positive charge stored on the gate is neutralized after several minutes to an hour of exposure time. A typical UV EPROM is represented in figure by a logic diagram. Its operation is representative of that of other typical UV EPROMs of various sizes. As the logic symbol shows, the device has 2048 addresses, that is 2 to the power 11, each with 8 bits. Notice that the 8 outputs are tri-state. To read from the memory, the output enable input must be low and the power down oblique program input should also be low. To erase the stored data, the device is exposed to high intensity ultraviolet light through the transparent lid. A typical UV lamp will erase the data in about 20 to 25 minutes. As in most UV EPROMs, after erasure all bits are ones. Normal ambient light contains the correct wavelength of UV light for erasure over a period of time. Therefore, the transparent lid on the package must be kept covered. To program the device, a high DC voltage is applied to VPP and output enable is high. The 8 data bits to be programmed into given address are applied to the outputs and the address is selected on inputs. Next, a high level pulse is applied to the CE/PGM input. The addresses can be programmed in any order. EPROMs. An electrically erasable PROM can be both erased and programmed with electrical pulses. Since it can be both electrically written into and electrically erased, the EEPROM can be rapidly programmed and erased in circuit for reprogramming. The two types of EEPROMs are the floating gate MOS and the metal nitride oxide silicon. The application of a voltage on the control gate in the floating gate structure permits the storage and removal of charge from the floating gate. Flash memories. The ideal memory has high storage capacity, non-volatility, in-system read and write capacity, comparatively fast operation and cost effectiveness. The traditional memory technologies such as ROM, PROM and DROM etc. individually exhibit one or more of these characteristics, but none of these technologies has all of them except the flash memory. Flash memories are high density read/write memories that are non-volatile, which means that data can be stored indefinitely without power. They are sometimes used in place of floppy or small capacity hard disk drives in portable computers. High density means that a large number of cells can be packed into a given surface area on a chip. That is, the higher the density, the more bits that can be stored on a given chip size. This high density is achieved in flash memories with a storage cell that consists of a single floating gate MOS transistor. A data bit is stored as charge or absence of charge on the floating gate depending if a 0 or 1 is stored. Flash memory cells. A single transistor cell in a flash memory is represented in figure. The stacked gate MOS transistor consists of a control gate and a floating gate in addition to the drain and source. The floating gate stores electrons as a result of a sufficient voltage applied to the control gate. A 0 is stored when there is more charge and a 1 is stored when there is less or no charge. The amount of charge present on the floating gate determines if the transistor will turn on and conduct current from the drain to source when a control voltage is applied during a read operation. Basic flash memory operation. There are three major operations in a flash memory: the programming operation, the read operation and the erase operation. Programming. As indicated in figure, initially all cells are at the 1 state because charge was removed from each cell in a previous erasure operation. The programming operation adds electrons to the floating gate of those cells that are to store a 0. No charge is added to those cells that are to store a 1. Application of a sufficient positive voltage to the control gate with respect to the source during programming attracts electrons to the floating gate. Once programmed, a cell can retain the charge for up to 100 years without any external power. Read operation. During a read operation, a positive voltage is applied to the control gate. The amount of charge present on the floating gate of a cell determines whether or not the voltage applied to the control gate will turn on the transistor. If a 1 is stored, the control gate voltage is sufficient to turn the transistor on. If a 0 is stored, the transistor will not turn on because the control gate voltage is not sufficient to overcome the negative charge stored in the floating gate. Think of the charge on the floating gate as a voltage source that opposes the voltage applied to the control gate during a read operation. So, the floating gate charge associated with a stored 0 prevents the control gate voltage from reaching the turn on threshold, whereas the small or 0 charge associated with the stored 1 allows the control gate voltage to exceed the turn on threshold. When the transistor turns on, there is current from the drain to the source of the cell transistor. The presence of this current is sensed to indicate a 1 and the absence of this current is sensed to indicate a 0. Erase. During an erase operation, charge is removed from all the memory cells. A sufficient positive voltage is applied to the transistor source with respect to the control gate. This is opposite in polarity to that used in programming. This voltage attracts electrons from the floating gate and depletes it of charge as illustrated in figure. A flash memory is always erased prior to being reprogrammed. So friends, that brings us to the end of our discussion in this lecture, and therefore we sum up. In this lecture, we learnt about ROM family and its organization. PROMs are basically the same as mask ROMs once they have been programmed. An EPROM is an erasable PROM. And finally, flash memories are high density read write memories that are non-volatile, which means that data can be stored indefinitely without power. So, that is it for today. See you in the next lecture with more on digital electronics. Thank you very much.